Thank you. So welcome. Good to have you back. How many of us made A in physics last semester? Let me see. Huh? A in physics. Have you checked your own? Where will you check your own? Do fast and check. I'll be getting good feedbacks. Even if I made B in A in mathematics, A in physics, A in practicals. Yes. The same thing with A1. AI. AI is getting A's like there's no score. So please, I want us to keep it up. Let me start with that Gauss theorem. Please check for me if this is the spelling you have there for Gauss. Double S should be no E. Gauss theorem. So I want us to start here. We are definitely going to electrostatics, going back to electrostatics. But I want us to understand this thing now that our brain is fresh. So this Gauss theory is centered on what we call electric flux. And in talking about electric flux, we know that electric flux is simply the collection of electric fields intensity. So in some books, in some textbooks, you see electric field. In some, you see electric field intensity. We will talk about all those things today. So if we know that electric flux is the collection of electric field intensity, Gauss theory is now saying that when we have this electric flux, that this electric flux that we have, notice the representation of electric flux is this way. If you have something like I here, you come and put something like this. So electric flux is collection of electric field intensity. Anything I will tell you electric field is, the collection of it is electric flux. When you have so many of it, it's electric flux. And that is why we have the first rule that this thing we call electric field line does not cross. The minute it crosses, it means that there's more than one electric field. So if I know that, this is saying that the collection of electric field is electric flux. Then Gauss theory is now saying that this electric flux that we know is equals to charge all over permittivity of free space. Welcome. AI. Lala. Welcome. So that is what his law is giving. That electric flux is equal to charge, ratio of charge to permittivity of free space. We are very sorry. Remember I said we are not starting here. I just want us to talk about this. Because we are just starting. Then we'll go back to electrostatics from the beginning. So he gave us this. And then you need to know that this permittivity of free space, anything permittivity in electricity or electric field, is simply talking about the differences in ability of electric field lines to travel. So the difference is, or you say, how easy it is for charges to move in an electric field is what we call permittivity. So the ability of charges to move easily is what we call permittivity. So there are charges that will move, maybe in a particular medium, will move somehow, some will move faster. There are some that are very good in the vacuum, some are not. So the ability or how easy it is for charges to move is what we refer to as permittivity. So I said the readiness of charge flow or of charges to move in an electric field is what we call permittivity. That's permittivity. So under this permittivity, we have relative permittivity, we have permittivity of free space, and we have permittivity of dielectrics. Hope you are aware. Those ones are chapter 1 works. So I said we have ER, chapter 1. we have this. For those of you that have gone through chapter 1, this is a common formula. So I said that this one is relative permittivity. Relative permittivity. This one is permittivity of dielectrics. If it's in a vacuum, it's equals to 1. If it's not in a vacuum, outside is greater than 1. While this one is permittivity of free space. I will say that it's 8.85 times. Okay, you still remember? Okay. So we'll derive the units. We'll get all the units. Because you know that this has units. Are you alright? Yes. So how we get the units is by when we get to electric field intensity, we'll make this subject of the formula. Then we get something there. So we are going back to that part. So if I know this, let's continue. And I said that this Gauss theorem is simply saying that this point, this electric flux is equal to charge per permittivity of free space, or the change, the integral of the change in electric flux equals to the integral in the change in electric field intensity times change times area. Yes, you see something like this, shouldn't? So this is the reason why I said let me start with this, because it's Rita that met me one time and said, "Sir, what is this? What is this?" So that's why I said let me put this thing out first. Once we are done with this, we'll go back and start the electricity. So please, what this thing is simply saying is there's integration here, there's change, and change means differentiation. The same thing here, the same thing here. Since I have it on both hand sides, this and this should take care of this and this. Are you seeing it? Go and check that in your textbook. So that is why anywhere you see electric flux, it is simply given as equals to EA. And even the unit of electric flux is simply, this is, what's it called? This one is electric field intensity, should be, which is in volts per meter. And this one is in meter square. So by the time you combine these two, you should get that your volts, let's do it this way. I have volts, then I have per meter. Let's check something. Volts per meter. I think square. Yes, for electric field intensity. We are coming there. Then I have area, and area is meter square. Is it not true? Yes. Yes. So that means that by the time this take care of this, I have volts. Stop. Is it not?
This thing, the electric field strength, I think it goes per meter, not meter.
Is it electric field intensity?
Electric field strength, yeah.
Electric field strength.
It goes per meter, not meter.
Are you sure?
Yes,
I doubt. Volts per meter. I feel. Because let's check something. That's why it's not even good to enter this thing first. I know that F is equal to KQ1 Q2 all over R squared. Then I know that electric field intensity is equal to force over charge. Should it? Yes. So if I have force over charge, E should be equal to KQ1 Q2 all over R squared divided by Q. Should it?
yes.
Over 1. Which means that by the time you turn it over, this is KQ squared.
Yes.
All over R squared times 1 over Q, right? This should take care of this. So E is equals to KQ over R squared. We are correct. We are correct. No, we should be correct. The one that should be, wait. Okay, but let's check something. If I know that E is KQ squared over R squared, should we? Let's check something because there's a relationship between volts and this. We know that voltage, I'm coming, is work done over charge. Voltage, I'm coming, that is V, potential difference, is simply work done all over charge. And notice what I'm coming, all over charge, work done over charge. And work done is Fs over Q. So that means that V is equal to F over Q. F over Q. Do you remember? Please remember, I'm supposed to teach you this first. Force of a charge is equal to E Q or QE. We take U to mean the sentence as mass. This one to mean the sentence as acceleration. So if that be the case, E is also the sentence as saying E equals to F over Q. Should we? Okay, so let's say that right here I see F over Q. So let me replace it with E. So E, S. And in electricity, S, this stance is taken to the R. So that means this is the sentence as ER. Should we? ER. So if that be the case, the vote is ER. The vote is ER. That means that
Sir.
I'm coming down. So remember, this is where we started having issues. So our issue is trying to get the units. So the unit of this. So we have E already. Look at this. We have E already. Let's say I replace this E now. This E now. Let's say I replace it. It will be the same thing as saying, let me clean this part. You've copied it now. We'll still do it, don't worry. Remember, we are not supposed to go to this. We are going back to it. I wanted to start with Gauss. So this is going to be E is equals to here V over R. Shall we? That is, if I make E solid of the formula here, V is equals to V over R. That means that if I replace here E with volts, this will be the sentence as saying I, that is equals to V over R. This is area, shall we?
Yes.
Then I have area is meter square. And remember that what I have here for R should be meter 2. Shall we? And then meter square. Okay. Okay. That means electric force is volts meter. Yes. Is this thing confusing? I are just copying. We are not supposed to get to this. Please forgive everything we did here. It's none of our business. We don't need to know it now. Our business is Gauss theory for now. Just go and write for me somewhere that electric flux is the same as saying volt meter. That's the only thing I want you to know. Every other thing here is none of your business. Just say we've all learned it, we will learn it. All these things are not your business. So I just wanted to get the unit of electric flux. So we said that electric flux is volts meter. So if I know that, that means that anytime you go to your textbook, this is why I started this thing first. Anytime you go to your textbook and you see all these integral signs, ignore it. All these things, ignore it. Just like that time we did first semester, usually you were paying attention to all those velocity and acceleration we were doing. You see that if you go to the textbook, there are parts where you see the changes in the first. So ignore it. So that means that this is what I just want you to know about electric flux. And this is what I want you to know. So this electric flux can be Q over E naught and also EA. I can have this formula as well. So I can say electric flux is Q over permittivity of free space is equals to electric field intensity and area. Are you seeing it? So it can also be this way. So have that in mind. So why am I doing this Gauss theory? Now this Gauss theory works for what we call a sphere. And this sphere is when I have, let's say, one charge. And there can be a situation where I have more than one charge. So please, let's say I have positive charge or negative. So if I have more than one charge, let's say 2, 3, 4 charges. These are the two cases you use Gauss theory. So either for a point charge, and when you have this point charge, you see that what you will have here, let's say you have that electric field line, your imaginary line, it will move this way. It always moves perpendicular at 90 degrees and move this way. So by the time you trace it, the Gaussian surface, it gives you a sphere. Are you seeing it? So if I have this, for example, let's say I have charges here, all these charges. By the time I trace electric field line here, electric field line, electric field line, electric field line, let's say I have the sensing here, the sensing here, the sensing here, the sensing here, the sensing here. Let's say I have something this way. By the time you trace this thing that is happening here, are you seeing this? Then, so it gives you something like a cylinder. So that is the two concepts of Gauss theory. Point charge, by the time you trace the electric field line, it gives you a sphere. Points of charges, different charges, by the time you trace the Gaussian surface, it gives you a cylinder. Two things. So the next thing now is to remember that the area of a sphere is supposed to be 2 pi, is it 4 pi r squared, should be? Because if you differentiate the volume of a cylinder, you get the area. Check for the volume of a sphere, you get the area. And I know that the volume of a sphere is something like 4 over P. Should be? So by the time you differentiate it, if 3 come here, it will be 12 over 3, should be? Pi, then 3 minus 1 is 2. So if go here, 1 should be? 3 go here, 1. 3 go here. So 4 pi r squared, yes. So anytime you differentiate volume, you get area. So that means that all I just need to do for point charge, remember I said Gauss theorem, all those things you see full textbook, it's just these 2 things they are trying to define for you. Point charge, you can take it the same thing as when they are talking about that infinity from a point to another. It's just these 2 things. So if I have for point charge, all I just need to do is come to this area, replace it. Notice that point charge gives me something like a sphere. Is it not true? That is, the Gaussian surface here is a sphere. Replace it with 4 pi r squared. Then I have my E equals to Q over E naught. When we come to this cylinder, I will show you. Let me clean this side so that you understand. Please note these things I said, so that you don't go to that textbook and be battling with integral signs. So we'll still do integration this semester, but it's good you know that once it's physics, those signs are not really here to bother you. So now if I do this, trying to make electric field intensity subject of the formula. Why am I always making electric field intensity subject of the formula? Because if you don't call it electric field intensity, you can call it electric field. Have it in mind. So when you call it electric field strength, it's the same thing. So it is always the key thing you are looking for. If you want to make charge subject of the formula, no problem. But I'm making this one from subject of the formula because most of the time that's what they are asking you to look for. So if I make this subject of the formula, you see that you now have E is equals to, or let's do it, anything starting on this one is over 1 cross multiply. So that I now have Q times 1Q equals to E 4 pi r squared E naught. And you know that E naught is permittivity of physics. Okay. So making inside the formula, we divide both sides by 4 pi r squared E naught over 4 pi r squared E naught. So that these will cancel this. So that E is equal to 4, charge. Yes, charge. All over 4 pi r squared E naught. The problem that students always have sometimes when reading this is that they want to read the whole chapter at the same time. Why I'm able to teach you this well is because I've done the course over and over. But when you are starting now, you need to section that your chapters into the chapter for electrostatics, the chapter for laws of this, the chapter that concerns charge. When you get to electric field, the chapter that concerns electric field, the chapter that deals with Gauss theorem, the chapter that deals with difference between potential difference and charge. So if you section it that way, it will be easy for you to understand it. Over and over, you now start combining the two as the same thing. So you see that I've gotten that electric field or electric field strength, electric field intensity is equals to Q over 4 pi r squared epsilon naught. Are you seeing it? Now there's something I will still teach you when we go back to electrostatics. Okay. When we go back to electrostatics, I will still teach you something. I did not start this class with electrostatics because I want you to grab this Gauss theorem. But we are going back to do all those things. Anytime you hear K, the constant here, that in our electrostatics class, we normally say that 1 over 4 pi epsilon naught. 1 over 4 pi epsilon naught is equals to K.
Yes.
And we normally say that it is also equals to 9. Exactly. It's very easy for me to remember. Do you know what I normally do? I just say everything is always times 10. This one stone is 9. Times it by 10. Raise it to 9 again. Finish. Are you seeing it? The unit for this, we can get it by doing all those our F equals to Q square over R square, and there's K here. By the time you make K subject of the formula, you get the unit from this. We'll do it in electrostatics. So for now, let's be ignoring the units. So when we get to our electrostatics class, we'll do it. So if I know this, that means that, notice that this thing can be rewritten as, I can rewrite this thing now to make the sentence and say, why I'm giving you this is so that when you go back to your textbook to read that Gauss theory, you are not stressing yourself. So I can write this thing here to mean E equals to 1 over 4 pi epsilon naught, then times Q over R squared. So that everything here now becomes E equals to K Q over R squared. Yes, that's what I want to get here. And you can now see that Gauss theory, with Gauss theory, when it has to do with a point charge or sphere surface, area of a sphere, that you are getting back your electric field intensity, which means that it's correct. So you need to notice this, very important. So that is all those things they are trying to prove there in your textbook is this thing. So now let's move to when there are different points of charges, which is for cylinder. So once we are done with this Gauss theory, we can now go back and start our class proper. Okay. Now for cylinder, I normally tell my students, anytime you have to maybe get the area, follow the other door, use the other door. I normally tell my students, that thing you normally do, maybe you go to AI or maybe browser, you search what is the area of the cylinder or maybe what is the area of a sphere. All those things might put you in trouble. The best way to find area when you are dealing with physics is simply find the volume of that particular thing you are talking about, differentiate it. That's the one physics needs from you. Like for example, if you do volume of a cylinder, check it for me. Check what volume of cylinder will give you. It should give you pi r something. Is it pi r square r? Volume of cylinder. Just check. What did he give me? So please, once we are done with our main class from the beginning, we'll solve all the exercise questions given at the back of that chapter 1. I try to tackle all of it. So the ones that are calculation, then the GST parts, I've made video on those ones. I've solved it. You will see me upload it. So check for me. Volume of a cylinder. Eh?
Pi r square h.
Pi r square h, you mean?
Yes, pi r square.
Anytime you are doing physics, once it's physics, you have to find area of something. If you can browse area of cylinder, and they'll give you like 2 pi r plus 2 pi h, 2 pi r h, you will get confused. So I normally tell myself, once you are dealing with anything with shape in physics, just find the volume, differentiate the volume. That's the area they want you to use. So if I differentiate this now, you see that this will be the same as saying 2 pi, that is 2 crossing over now. Carry the power, multiply to be 2 pi r, then 2 minus 1. Should be like this. Then notice that there is edge here. Then this edge becomes length. Why am I using length? Notice that it's the same thing. If I'm not using height, I can use length. So, but why am I using length? Notice that if I have this to be my point charge, this shape that I've got in here, point charges, point charges, point charges, point charges, point charges. When I have more than one charge, and I said that there is a rule. One of the properties of electric field is that the imaginary line moves in 90 degrees to the charge. That one you normally see, maybe they come and do something like this. Come and do is just to show repulsion or attraction. But once it has to do with the electric field, and it's always move So if I know this, if I get this shape, let's say this is the cylinder now. I get this shape of this cylinder. All the things that concern this electric field will simply be flowing up. And then that is the charges will be exerted this way and this way. Are you seeing it? So the charge will move this way. This one is going outwards this way. And the one going this way. So if that is the case, the only thing I'm simply considering for this cylinder is simply all the charges acting on this axis. And then this length. That is more like I'm having this and this end. Remember that this is curved because it's a cylinder. So everything on this end is what I have. The length and this. So this side gives me 2 pi r and this side gives me L. Hope you are taking note of this. Very important. So that is just what I need. So for when it has to do with point charges, the area I'm using is simply equals to 2 pi r L. That's what I want you to note. Notice that when it's a point charge, the area I use is 4 pi r squared. Do you remember? So that's what I'm trying to do here. Then, yes, then again, notice that when it's a sphere, when I have this sphere, I didn't check the density, the inside. But this one I had to go inside. Like a cylinder now, I had to go inside. So if that is the case, what we are checking here in this case is what we call the linear density. Linear density. Something like this. We use lambda for it. And we say that linear density. Normally we know that in physics, density is mass over volume, should it?
Yes.
Do you know that we have linear density, which is mass over length?
Over length.
Mass over length. When we did moments, if you remember when we did moments, then we did how to find moment of rigid bodies. If you still remember, we did where we've used different formulas of deriving that of a sphere, differential disk, all those things. So when I have that, assuming I use mass, I have mass over length, that is linear density form. But once it's charged, I told you that you should always consider charge to be the same thing as your mass. Have it in mind. Once it's an electric field, you consider. So this is going to be simply Q over L. Q over L. So you write somewhere in your notebook where this is the same thing as linear density. Linear density. Why am I using linear? When something is talking about linear or length, it's simply talking about one axis, either going this way 90 degrees or going this way. So I'm not using area. Area talks about the two directions at the same time. While volume talks about this and this. So for length, I'm considering just this or just this. That's what I'm looking at. So if I know this, if I make charge subject of formula here, you see that I have Q to be equals to, sorry, but normally using this way, Q to be equals to lambda times L. Is it not true? And remember that this is our formula. This is what Gauss theorem is talking about. The summary of what Gauss theorem is talking about is simply that electric flux is equals to charge over permittivity of free space, and that electric flux is also electric field intensity and then the surface, which we call the Gaussian surface. So in summary, this is the formula for Gauss theorem. This is something you need to note. So, but when you are now thinking of different surfaces affected, if it's one point that is fair, you use the first formula. If it is now point charges, which is cylinder shape, cylinder surface, which we call Gaussian surface in that case, you use this one we are going to derive now. So what I will simply do is that for a cylinder, Q is not just what I'm going to have there. Rather, I will replace Q with this lambda and L. Are you seeing it? Yes, if you go to textbook, if you go to your textbook, please, if you go to your textbook, you see that all those things that they're solved, all those things where you see things like, maybe they're putting things like this. Things like this. So, if you look at it, you see that this lambda, if they did not use this lambda, they will use something else, but it's still the same thing it's talking about. So don't get confused about it. That's what I mean. So I will use this to replace Q. Please, when it has to do with cylinder, I have to look for the linear density. That is just the only addition here. Then replace Q with this. Inside that Gauss theorem, we'll solve for E, we'll get our final answer. So if I want to now get the Gaussian theory, I will go back and quote it. I'll simply remember that he said that charge over permittivity of free space is equals to, yes, very simple. Somebody will be somewhere looking for this one and this one. You've already gotten that one, so never put it. So I'll replace charge with lambda L all over E naught equals to E. Now, the area for a cylinder is going to be 2 pi r L. Very simple. So if I make this subject of the formula, this crossover, so that I have lambda L is equals to E 2 pi r L E naught. Maybe this subject of the formula, divide this as by 2 pi r L E naught. 2 pi r L E naught. This will cancel this. And notice something, there's L here. There's L here. I can cancel this. So that E now becomes equals to lambda over 2 pi r E naught. So if somebody wants to write it, you can even see it in the textbook where they write it as maybe lambda over 2 pi E naught r is the same thing. So with this, we've treated all those things you see them talking about when it has to do with Gaussian theory. So please, I want us to go and start this class from the beginning. Why I started this first is because it's the only part that might confuse you if I start it late, because of all these things you are rotating. So, but I believe now, if you go and read it properly, it will make sense to you. Anywhere you see density there, if you don't want to use this, you can use the other one. It's the same thing. I know that what they're talking about is linear density. Okay. So please, with this, I want us to clean and start. So you write chapter 1, electrostatics. So we'll try our best to do all the chapter 1, solve all the textbook exercises, calculations on chapter 1, then treat chapter 2, then revise chemistry chapter 2 that we did. So this was all about Gaussian theory, Gauss theorem.